So here's some information about solutions for you. By this point in time, you should be pretty proficient at working with solutions. We have our little chemistry cat here with her solution joke. But you should be good at working with solutions. You should be very comfortable with all of the solution vocabulary. And we're working on now calculating concentration by molarity. So here's some of the things that you should definitely already know. You should know a lot of solution vocabulary, solute, solvent. You should know about how solutions form. You should know words like saturated, unsaturated, supersaturated, be able to recognize those on a graph. You should know the different factors that affect solubility. We have worked on those. You should know about electrolytes, and you should be good on calculating concentration with mass percent. And hopefully after this video, you'll be good with molarity. So remember, as we're looking at solutions, these are homogeneous mixtures. They're the same throughout, not heterogeneous mixtures. All right, so let's do a quick little review. So number a piece of paper from 1 to 7. As you're done, we're going to check your answers here. You'll also tell me how you did on that on Schoology. All right, so what would you say this is right here? Question number 1. Sorry, that should have a 1 by it. Jot down your answer. All right, so what'd you say? If you said a solution, you are exactly correct. Let's look at questions 2, 3, and 4. Look at this solution. It's in the flask. We have a zoomed in view of this solution so you can see the solution on a molecular level. So what's the solvent? What's the solute? And what does the solute form as the solution is made? All right, so what'd you say for question 2? If you said that water is the solvent, you are exactly right. We know that because it says right down here at the bottom that it's an NaCl aqueous solution. And so what is the solute? Hopefully you said NaCl. And when that NaCl dissolves in the water, what does it form? Yes, ions, which we also call electrolytes. Okay, here's questions 5, 6, and 7. Another solution. What's the solute? How many particles are in this solution? And then how many NaOH particles were dissolved? All right, so what'd you say for number 5? What's the solute? Hopefully you said NaOH, sodium hydroxide. How many particles are in this solution? Hopefully you said 6, and you are exactly right, because remember, as we're looking at concentration and molarity, we're talking about the number of particles. And how many were actually dissolved? Only 3. And as they separated into those ions, there they are. Oh, I guess we won't need to do 8 and 9 because they didn't animate. So if you take a look there at what's going on, you can see the person diluted the solution, but the number of solute particles, if you count them, it stays the same. Because remember, in chemistry, we're all about the particles. We're all about the solution on a molecular level, and we count those number of particles in moles. Okay. Here's a little bit more of a quick review. Solutions have 2 parts. What are they? Hopefully you said the solute. And that's the part that does what? And the solvent. And what part is the solvent? Hopefully you said that the solute dissolves. That's what gets dissolved in the solvent. Does the dissolving. Often a liquid, and often we use water. How well it's dissolved is solubility. Now, what does solubility depend on? Hopefully you were thinking the temperature and the type of solute. When we graph solubility, and we've made those solubility graphs, the lines are usually, hopefully you're thinking curved. And you remember making those solubility graphs. Why is water often used as our solvent? Because it is really good at unlocking ions to form electrolytes. And these electrolytes are able to conduct electricity. There's 3 different strengths of solutions. Hopefully you're thinking dilute, because it has very little solute, like a weak Kool-Aid solution. Concentrated, which has a lot of solute, like a cleaning chemical. And a saturated solution. A saturated solution, remember, is very specific. It can't hold any more solute, like really good Kool-Aid. So if we look at how solutions conduct electricity, when something that has ions dissolves, they don't stay together. They unlock or dissociate to form electrolytes. Like, for example, this solution right here earlier that we saw earlier in today's class. And then don't forget, when we're looking at these particles of solution, if we have a mole of particles, that is what we would call Avogadro's number, 6.02 times 10 to the 23rd. All right, so let's get started with concentration in molarity. Remember, it is the number of moles of solute per liter of solution. All right, and so if we have an equation like this down at the bottom, this example, what is the molarity of H2SO4 if 1 mole of H2SO4 is present in 250 milliliters of solution? Oh, and that should say of solution. So the first thing we're going to need to do is take a look at what the problem gives us. So we have 1 mole in 250 milliliters of solution. We know that our formula for molarity is moles per liter. And hopefully that will move along. So make sure that you recall that equation. Hopefully you do have that in your notes, that molarity, big M, equals the moles of solute divided by the liters of solution. So when we have this problem, like we have right down here, we know that we have 1 mole of solute in 250 milliliters of solution. And so the first thing we need to do is turn 250 milliliters into liters. And so that will be 0.25 liters. And so we're going to simply write this formula again. So I always write that each time. So our molarity equals moles divided by liters. Now I think my liters are hanging off the bottom of my screen here. Oh, there we go. You can see it a little bit. And then I simply substitute in. I know based on what's in the problem that I have 1 mole of H2SO4 and 0.25 liters. And then I simply do the math. What's 1 divided by 0.25? And so this is a we would say big M or molar solution. Let's try another example. How many moles of glucose are needed to make 125 milliliters of a 0.5 molar solution? So this one is a little different. And so once again, if I'm looking at the problem, so pay attention to my ink because it will disappear, is I'm trying to find moles. And I haven't had to do that yet before. So I'm looking for the number of moles. I know that I have 125 milliliters of solution and the concentration. I know the concentration as well. And so I'm going to once again start with my formula. Remember that formula is the molarity equals the number of moles per liter. And so I know that I have my molarity and I have my I have milliliters, so I need to change that into liters. And so I'm going to be looking for moles here. So you can make moles X, or you can rearrange the equation in terms of moles. It doesn't matter how you do it. And so today I'm going to go ahead and rearrange that equation. I'm going to multiply both sides by L so that I know molarity times liters equals our number of moles. So now I simply need to turn my volume into liters, 0.125, times the molarity. And when I do that, as I do that math, remember that the molarity, big M, is moles per liters. So notice that my liters will cancel out here. You can see them canceling out here and here. There they go. And so when I do the math, 0.5 times 0.125, I've got 0.0625 moles of glucose. Now, of course, if we go into the back to measure this glucose, I know how many moles I've got, but can I measure in moles? No, we cannot. So we would always have to convert these number of moles into grams. So this is where your periodic table comes in super handy. So if you look at your periodic table, you'll see underneath of carbon that number 12. That tells us that 12 grams of carbon is equal to 1 mole of carbon. In this case, though, I don't have just 1 carbon, I have 6. So you would simply multiply that by 6. Eventually, you would add these all together, and I could do the same thing with my hydrogen. If I look underneath of hydrogen on my periodic table, I'll see that it has a mass of 1, and that's again 1 gram per mole, but I have 12 hydrogens here. And so I would put that together. Then I would look at my oxygen. I see that under oxygen, it's 15.999, so I'm going to round that to 16. And I have 6 oxygens here. Now, once I do those multiplication problems, then add that all together, I'm going to get 180 for my molar mass for glucose. So what does that mean? That means that 1 mole of glucose is 180 grams, or that 180 grams is 1 mole of glucose. What else that tells me is that if I make this solution, if I were to put in 1 mole of glucose, then I would have 6.02 times 10 to the 23rd particles of glucose. All right, so remember that number, 180 grams. And what I can do here is simply take that number of moles and multiply by 180. Notice my moles are going to cancel here. And then I would have 11.25 grams of glucose. So if I were to make this 0.5 molar solution, I only need 125 milliliters of it. I would need to get 11.25 grams of glucose. So those are our couple of molarity practice problems for class today. I've got a Schoology assignment for you to do where you're going to do some molarity practice problems on your own. Like I said, don't forget that is our molar mass from the periodic table. Oh, I forgot I have one more problem for you. I'm so sorry. All right. So this is a solution. It's called Tris Buffer. It's used in a lot of hospitals to adjust the pH of people's blood. So how many moles of Tris Buffer would we need to make 500 milliliters of solution? And it's got to be a 3 molar solution. So again, let's take a look at the problem. All right, so once again, I'm looking for my number of moles. I see that I have my volume, but it's in milliliters. And I see I have my concentration in molarity. All right, so make sure you think about that, because as soon as I click the next button, it's going to erase that drawing. So we're going to have to remember, I'm looking for my number of moles. I have my volume, my liters. I got to just turn it into liters. And I have my molarity. So once again, I'm solving for moles. So I can make this moles X. I can solve it like that, or I can rearrange it. In this case, I decide to rearrange it again so that my moles, hold on. First, I did my volume. I turned 500 milliliters into liters. And I've rearranged it so that I know that my moles equal my molarity times my liters. And now I know I've got 0.5 liters. So I simply substitute in. I know I've got 3 molar solution times 0.5 liters is my number of moles. And so when I do that math, 3 times 0.5, I get 1.500 moles of this buffer. So if I wanted to make up this buffer, how do I go and get it from the lab? Yes, I have to measure the mass of it. And so once again, I could do the molar mass of this buffer just simply looking at my periodic table, because I know that my carbon is still 12. It's always 12. And I know that I have 4 carbons. I know that hydrogen is 1, and I see that I have 1 hydrogen, or 11, excuse me, hydrogen. So 1 times 11. I know that nitrogen, let me look at nitrogen on my periodic table. Nitrogen is 14. And oxygen is 16. So I can do all of this to figure out. I've only got 1 nitrogen, so that's easy. And my oxygen is 16, and I've got 3 oxygens. And so when I put all of that together, I'm going to come up with a number that tells me the molar mass of this tris buffer. And that number is going to be, hold on, it should be coming up right here, 121 grams per mole. That's our molar mass. Notice that our moles are going to cancel out again. Well, it didn't show it. Sorry, my lines are in the wrong spot, it looks like. But when I multiply 1.5 times 121, I get 181.5. So that means if I needed to mix up this buffer, if I was working at the hospital, I'd have to get 181.5 grams of that tris buffer and then dissolve it to 500 milliliters, or half a liter. Now that is our last practice problem. I hope this helps you as you're working through some molarity problems. If you have any questions, just let me know.